This video will cover section 2 of chapter 8 on sampling distributions working with means. We'll look at what a typical inference problem will look like when we're working with means. We'll use 3 approaches to understand the distribution of means. We'll talk about how to find the center, the spread, and the shape of the distribution of sample means. And we'll use the empirical rule and talk about other ways of finding, ways to evaluate means that we find. So in the 4 stages of statistics, we are in probability, and we're talking about sampling distributions and means. So here's what a typical problem looks like. If you take all the numbers from 1 to 20, you'll note that they have mean 10.5 and standard deviation 5.8. You can find that by entering those numbers into your calculator. If numbers picked at random, and we're putting that in quotation marks, by a sample of 400 students, if the mean of the sample is 11.6, does this suggest that the students were biased to pick higher numbers? Here's how we're going to get at this. If we assume that the population mean is 10.5, what we'll do is we'll find the probability of seeing a sample mean as high or higher than 11.6. If that probability is really low, then it'll be hard to believe that the population mean actually is 10.5, which will mean that the set of numbers that the students were actually pulling from was different from the numbers from 1 to 20. So they weren't giving each of the numbers from 1 to 20 equal consideration, is the way that we would interpret that. So let's get at that idea of a probability. So here's how we're going to do this. If we know the population mean, mu, and the population standard deviation, sigma, and we have a sample size n, what we want to do is find the probability that a sample mean, and that's a capital X bar, we want to find the probability that the sample mean is in a certain range. To do that, we need to know how X bar, the means of our samples, are distributed. Now, a notational comment. Little x bar denotes a single statistic, so that's a single value. Big X bar, that's the mean of the random variable. It's important to be able to draw the distinction between those two. Now, remember that a sampling distribution of a sample statistic, we've already looked at the sampling distribution of sample proportions. Today we're looking at sample means. That's a different statistic. Sampling distribution talks about the way that the probability distribution of values that the statistic can take, how that gets distributed if we were to repeat the random samples of that fixed size a whole bunch of times. Again, in the previous section we talked about sample proportions. So we're going to cover much of the same territory, except now we're talking about sample means. There are 3 ways to get at this. We could use intuition, we can use hands-on experimentation, and we can use some theoretical results. We'll do much like what we did in the last video. Now, let's look at an example to start building our intuition. Here we're looking at rolling a single die. Since there are 6 equally likely outcomes, the probability histogram looks like what you see at the bottom. What is the shape of the histogram? Well, we can see every bar has exactly the same height, so we would say that this histogram has a uniform distribution. Being able to identify the shape of the distribution in the population will help us identify what the shape of the sample mean distribution is for different sample sizes. Now, if I roll a die, overall the mean in the population is 3.5. That's what you get if you find the mean of the numbers from 1 to 6. So here are questions we might ask. Is the underlying variable, that is the result we get on the die, categorical or quantitative? What happens for repeated rolls? So if we roll the die, we say we're going to roll it 4 times. what is the mean going to look like? If we roll it 10 times, what is the mean of all of them going to look like? What type of variable is this? The mean inside each of our samples. Finally, what three aspects of the distribution of the sample mean should we report to summarize its behavior? Well, the underlying variable, we roll the die, we get a number between 1 and 6, so that's quantitative. What type of variable is sample mean? Well, we're taking the mean of a bunch of numbers, that's making it quantitative. And it's a random variable because its value depends on some random process. Finally, if we're going to talk about the distribution of the sample mean, we need to talk about center, spread, and shape. Here we see the histogram that we saw earlier for the outcomes when we roll a single die. Now this little applet will let me simulate a whole bunch of die rolls. So let's roll this die 100 times, and you can see what we actually observe in our outcomes. You can see that our we actually rolled a 6, much less than the others, only 8% of the time, whereas we rolled a 1 a full 2% of the time. But in the long run, as we keep doing this, notice that those differences start to kind of even out. And if I jump this up to 1,000 rolls, you'll see experimentally that the percentages of each seem to be closing in on the ideal percentages that are given by the blue bars. Now the question is, what happens as we increase the number of dice that we roll? Let's jump up to 2 dice. So if we roll 2 dice, and we look at the average that we see on the 2 faces. Well, if I roll once, there's a 4 and a 5, that's a 9, and there you see our bar above 9. Oh, actually, no, that bar is not above 9. That bar is above 4.5 because that's the average of 4 and 5. So here our average can go anywhere from 1 to 6. So let's do this again. We got a 2 and a 5. The mean there is 3.5, and there you see our bar above 3.5. So what happens if we do this a whole bunch? Let's do this another 1,000 times. And what do you see happening in our distribution here? It's starting to look almost like one of those Mayan pyramids with the steps, right? We do another 1,000. Here we see the most common values right there at that peak. That's at 3.5. And then it tends to sort of taper off, not like the normal distribution would, like curved. It almost looks straight as we go down. If I tack on the ideal, like the theoretical histogram, here's what it looks like. And sure enough, that tails off like a line, like linearly on either side. So let's bump this up a little more. Let's look at 6 dice. If I roll 6 dice, here I got a 5, a 4, a 1, a 1, a 4, and a 5. That works out nicely. The average of those is 3 1/3. And there you see our bar above 3 1/3. We do this again. There's a 1, a 2, a 5, a 4, a 1, and a 3. That averages 2 2/3. And there's our bar. Let's do this a whole bunch and see what our distribution starts to look like. Here it looks like we're forming a peak above, well, maybe somewhere near the middle, about 3.5 again. This doesn't look like it tapers off linearly, but it's not linear. It's actually looking like it's more curved. So let's do this for another 1,000 times, see if that bears out. So our peak seems to be staying put right here above 3.5. let's tack on the ideal distribution, and sure enough we see it tailing off from our peak, not linearly, but it's flatter at the top and steeper on the sides, flat again at the ends. So it looks like this is approaching a normal distribution. If I throw in another couple of dice, maybe 8, let's just go ahead and run this a whole bunch. And you see more or less the same shape taking place. Here, peak above 3.5. Here's our ideal histogram. Some of these are above what we expect, and some are quite a bit below. That one's way below. But as this keeps running, we'll see it slowly start to move up toward where it wants to be. So as we keep rolling and keep rolling and keep rolling, it looks like the distribution of the numbers that we see is approaching something that looks kind of normal. So let's dive into some of the theory. If we take random samples of size n from a population with mean mu, then the sample mean is 1 over n, that's the number we chose, times the sum of the values that we actually observe. Now each of those observed values is random, and the mean is mu. So if the this first value that I'm circling here has mean mu, and the second value has mean mu, and the third value has mean mu, and the fourth value has mean mu, then all those together, the average ought to be about mu. And I've got n of them, so I add those together, these n terms. I get n times mu, and I still have that 1 over n out in the front. Those cancel out, and that gives me just plain old mu. Now for the standard deviation, remember that the mean x bar, big X bar, looks like this. We expect each of x1, x2 up to xn to deviate from its mean by about sigma. But remember, we can't add standard deviations together. The thing that adds together is the variance. So what I need to do is find those variances and add those together, and then take the square root to find the standard deviation. There's some algebraic stuff that's going on here, but the thing I want you to take away is this formula right here on the end. The standard deviation for sample mean is the population standard deviation divided by the square root of the sample size. Now remember, we have a rule of thumb for when these things will be approximately normally distributed. For that to happen, in order to use that formula for the standard deviation in particular, we need these, the selections, our sample choices, to be approximately independent. And in order to get that approximate independence, the size of the population has to be at least 10 times the size of the sample. Now, for means, we don't have a rule of thumb that works for approximate normality like we did for proportions. Remember, for proportions, we just needed n times p and n times 1 minus p to both be at least 10. We don't have something quite so simple for sample means. That being said, remember that the central limit theorem tells us that any sample statistic that we look at, as long as we take our samples big enough, the distribution will be approximately normal. This is something that makes intuitive sense. We've kind of seen it a little bit. With our experiments that we saw with the dice rolls, we saw that histogram approaching normality. We're not going to prove it. We need some really advanced stuff to do that. So what can we say about the shape of this distribution? Well, we will be able to say that the shape of the distribution of sample means is approximately normal if one of these holds. If X itself is distributed normally, then the mean of samples will also be normal. Or if X is fairly symmetric and N is at least 15. Or N is moderately skewed and N is at least 30. So fairly symmetric might be something like this, where there's a little bit of a tail on the right. Moderately skewed might look a little bit more like this, where there's a really heavy tail on the right. So, remember, for a random sample of size n from a population with mean mu and standard deviation sigma, these are the mean and the standard deviation for the population. The sample mean x bar has mean mu also, and standard deviation is sigma divided by the square root of n. The shape is approximately normal if n is large enough, and large enough depends on how our original x is distributed. Something that's very important to note. When we're looking at the sample mean x bar, the mean of our sample is equal to the mean of the population. So this mu is talking about the population. This mean is talking about the sample mean. Since those two are equal, we say that x bar is an unbiased estimator of mu. This is only true if the sample is random. So as long as our samples are random, I can expect x bar to be close to the population mean. This is something we're going to rely on very heavily when we start with inference. In inference, we won't know what the population mean is. We only have a sample mean. Since the sample mean is an unbiased estimator, we can use the sample mean to approximate the population mean. Now, the standard deviation of our sample mean is the population standard deviation divided by the square root of n. Because that n is in the denominator, the bigger the sample size, the less spread we'll see in the sample means. Remember, for the dice we saw earlier, the mean tended to be around 3.5. That's where the peak was every time. But as the number of dice went up, that peak became more and more pronounced. More and more data were cluttered around that mean, and the tails became less pronounced. Remember, for this formula for standard deviation, the size of the population needs to be at least 10 times the size of the sample. We'll also need this when we start on inference. The bigger the sample is, the better our estimate will be for the unknown population mean. Now, the shape is approximately normal as long as n is large enough. Because it's approximately normal, we can find probabilities using the normal distribution. This is what we're going to use to solve problems about inference. So let's look back at sample mean when we're rolling 2 dice. Remember, a single die has mean 3.5 and standard deviation 1.7. So what can we say about the sample mean x bar? Well, the mean ought to also be 3.5 because 3.5 was the mean for the population. For the spread, we use the standard deviation, which is not the same as the population. We have to divide by the square root of the sample size. In this case, n is 2, so 1.7 divided by the square root of 2 is about 1.2. As for the shape, we can't say that it's approximately normal. Since the population, remember, it has a uniform distribution. That's not normal, so the first rule isn't satisfied. n equals 2 is a small sample size. It's not big enough to use either of the other two criteria. Now, this isn't skewed at all, right? The tails are exactly the same, but we need a population of at least probably 8 or 10 for this to be approximately normal. For 8 dice, the sample mean, again, I would expect to be 3.5, because the sample mean and the population mean are going to be the same. The spread would be the standard deviation. Now, instead of dividing by the square root of 2, we divide by the square root of 8. So notice that the spread has in fact gone down quite a bit. As for the shape, 8's getting kind of borderline on normal. So it's definitely more normal than when we were only rolling 2 dice. Now, a quick refresher about the empirical rule, the 68, 95, 99.7 rule, for a normally distributed random variable. Remember, there's a 68% chance that our random variable is within 1 standard deviation of the mean, 95% that it's within 2 standard deviations, 99.7% that it's within 3 standard deviations. We can extend this to sample means, since sample means are a random variable, as long as they're distributed approximately normally. So, if the population mean is mu, so again, that's coming out of the population, and the standard deviation is sigma, also coming out of the population, the 68, 95, 99.7 rule says that 68% of the time, our sample mean will be within 1 standard deviation for sample means. Notice we're not just using sigma there, it's a different standard deviation. Within 1 standard deviation for sample means of mu. We can say similar things for 2 standard deviations for sample means and 3 standard deviations for sample means. Remember, this is only true if n is big enough to guarantee that the distribution is approximately normal. 8 dice is enough. So remember, for a single die, the mean is 3.5 and the standard deviation is 1.7. So the sample means are distributed in a way that has mean 3.5, and again, this is for x bar, and standard deviation 0.6. Remember, that's 1.7 divided by the square root of 8. That's what that 0.6 is. And 8's big enough so that this is fairly normal. So the rule tells us that there's a 68% chance that the sample mean is within 1 standard deviation for sample mean of 3.5. So going up and down by 0.6, we get the interval from 2.9 to 4.1. By going up and down 2 standard deviations, we get that there's a 95% chance that x bar is in the interval 2.3 to 4.7. And going up and down 1 more standard deviation from there tells me that it's a 99.7% chance that our sample mean is in the interval from 1.7 to 5.3. So, remember our typical problem that we saw at the beginning of this video. If you look at just the numbers from 1 to 20, the mean is 10.5 and the standard deviation is 5.8. If we ask 400 students to pick a number between 1 and 20 at random, and the mean that comes out is 11.6, does this suggest any bias, that students were picking not at random, but were picking numbers that were higher than random? So remember, the method that we mentioned was to assume for the moment that the population mean is 10.5. So here when I'm saying assume that the population mean is 10.5, I'm talking about the population that the sample is coming from. If this sample is abnormally large, that means that the students aren't choosing from the population that we think they are. So we want to find the probability that our sample mean is as high or higher than the one that we observe, 11.6. So we've already talked about how to find these probabilities. So let's look more closely. So here's our question. For this random variable x bar, what are the mean, standard deviation, and shape? Well, again, if we assume that the mean in the population is 10.5, then x bar ought to have mean 10.5. Since n is 400, that means the square root of n is 20. So the standard deviation for x bar would be 5.8 divided by 20, which ends up being about 0.3. And 400 is a very large sample size, so that's going to be very normal. So let's look at our assumption about the population mean. Since this sample is big enough to be approximately normally distributed, then the mean of our distribution ought to be 10.5. The standard deviation for this distribution, again, of the sample means is 0.3. So we're going to go up by 0.3 and up by another 0.3 and up by another 0.3. Now, where is our sample mean? It was 11.6. 11.6 is way out here in the right-hand tail. It has a standard value, a standardized value, a z-score, bigger than 3. So the chances of getting a sample as weird or weirder than that one is less than 0.0015. So we're going to say that that's lots of evidence that there is some bias here. So remember, for another example, IQ scores are normal. The mean is 100. The standard deviation is 15. Is 88 an unusually low number for an IQ of a single randomly chosen person? What about for the mean of 9 randomly chosen people? For one randomly chosen person, we can standardize. We take our observed value of 88, subtract the mean, divide by the standard deviation, and we get negative 0.8. So that's not even one standard deviation below the mean, so that's not terribly unusual. If we choose 9 at random, again, the mean of the averages ought to be 100. For the standard deviation, we take the standard deviation of the population, which is 15, but we're going to divide by the square root of the sample size. So the square root of 9 is 3. That gives us a standard deviation for this sample mean of 5. So standardizing using 5 as the standard deviation gives us a z-score of negative 2.4. That is an unusually low z-score. Looking at this graphically, for an individual person, 88 falls right about here on the normal curve. It's pretty close to the middle, so that's not terribly low. But when we look at sample means for a sample of size 9, notice that one standard deviation is now 5 instead of 15. And a value of 88 falls way back here. Since it's way down in the left-hand tail, that's really unusually low. So here's another problem. Household size X in the United States has mean 2.5 and standard deviation 1.4. So is 3 an unusually high household size for a single household? What about if we choose 10 random households and take the mean? What about the mean of a sample of 100 households? For a single household, we can't use this rule. The reason why is 3 is a small sample size, so I don't know that this is distributed normally. We can conclude, though, that since 3 is pretty common, it's very close to the mean, I'm not going to think that that's unusually high. But keep in mind, I'm not basing that on the normal distribution. For size 10, here I'm expecting this to be really right skewed. Why? Well, if you think about what the possible values are, let me draw you a picture. We could have 0. Actually, 0 doesn't make any sense in this context because then it's not really a household. So 1 is the minimum value we could have. We could have 2, we could have 3, we could have 4, we could have 5, we could have 6. So 1 is people living alone. I expect that to be about that tall. 2 would be like married couples with no kids or single parents with 1 kid. I expect that to be bigger than 1, but not significantly bigger than 1. So 3 might be 2 parents with 1 kid or 1 parent with 2 kids. There's 2 parents with 2 kids or 1 parent with 3 kids and so forth. Do you see how this is looking pretty strongly skewed to the right? Since it's so strongly skewed to the right, 10 is not a big enough sample size to get that this is normal. 100, though, that's going to be big enough. So the sample means would be distributed in such a way that the center, the mean of the sample means, would be 2.5. That's the same as the mean in the population. The standard deviation would be the standard deviation in the population divided by the square root of the sample size, which gives us 0.14. So if we standardize this value of 3, we get 3 minus 2.5 in the numerator, divide by this new standard deviation for the sample means, and we get a z-score of 3.57. That is crazy high. So to sum up, we talked about what a typical problem is going to look like when we're doing inference for sample means. We looked at several different ways of understanding the way that sample means are distributed, intuitively, with an experiment, and theoretical. We talked about the center, spread, and shape of the distribution of the sample mean. We talked about applications of the empirical rule for sample means. And of course, we also know how to use our calculators and computers to find areas under the normal distribution using normal CDF. We went back to our typical problem and looked at how we're going to approach solving it. And we also gave an example of checking the assumptions that we have to make in order to use the rule.